thank you for joining us for Iris Media Day. I'm Aaron Opperly. I'm the Senior Director of Media Relations for the School of Computer Science here at Carnegie Mellon University, and really excited to have the Iris team today share with you their project. So to kick us off, though, I want to have Matthew Johnson Roberson come up and welcome you all. So he's the director of the Robotics Institute. Matthew?
Thanks. Thanks. Well, I wanted to welcome everybody on behalf of the School of Computer Science. As Aaron just said, my name is Matthew Johnson Roberson, and I'm the director of the Robotics Institute here. And this is very exciting. And so I wanted to take a moment to thank you all for coming, but also to say that this is like a really special moment for the students that are involved. And I know that because I was here as a student many years ago, and the opportunity to work on projects like this are really inspiring. And things like this change the course of where your life heads. So when I came here when I was 20, I didn't really know what I wanted to do. I got into robotics. I got the opportunity to work with Red, who you'll hear from in a moment. And that really changed the course of the rest of my life. I got excited about robotics, and I think that was in no small part to what I got to do here at CMU. Anyway, so I wanted to say that you're going to see a bunch of cool technology, but most importantly, you're going to probably get the opportunity to interact with a bunch of really interesting and excited students. And I think that is the secret sauce of what we do here at Carnegie Mellon. And the opportunity to work on real projects that do real things out there in the real world is really at the core of what the Robotics Institute is about. And we are really, really proud of the work that these students have done, and really, really excited to give you an opportunity to see it. I'm going to hand it off to Red, who's one of my mentors, and he has done so many different things in robotics. It's very hard to pin it down. But I think he's going to be really excited to tell you about what they're doing in space, and that's the sort of next frontier of his career. So without further ado, Red Whitaker.
So Carnegie Mellon Robotics has pioneered land, sea, air, underwater, underground, and space is our next frontier. We've actually led U.S. space research and been NASA's premier partner in the area for a third of a century. And in the course of that, pioneered the very first autonomous research version of a lunar explorer. The one in the upper left was a long-distance 200-kilometer trek in planetary-like desert in South America. The upper right is the vertical arrays that go with a polar rover. The lower left, a lander. We're not just rover guys. And in the lower right, the one we're now preparing for our next mission, which will go to the pole of the moon to look for the ice. Of course, it's always about the people, and there have been hundreds of them that moved from here into every major company all over the NASA agency, and of course, here at home. One of my favorites is in the lower right, where alumnus Tony Spear led and landed the very, very first of the Mars missions. In space, what counts is what flies. And the significant thing for what we're going to see next is that by this flight, Iris transforms CMU into a spacefaring institution. Now, we see the real deal. Here's Iris.
Hi, I'm Raywin Duvall. I am the Iris Program Manager here at Carnegie Mellon, and I am a research associate under Red, who you just met. So I'm here to talk about Iris as a program and what we are. Iris is going to be the first university-built rover to leave Earth, and the first lunar rover not made by a national space agency, which is a huge deal. But the biggest thing that we are going to be as a university rover is we're also going to be the first American robot to be driving on the moon. Obviously, we've sent the U.S. has sent a buggy that the astronauts drove up there, but we are going to be that first American rover. Over 300 students have been partaking in Iris over the years, have helped make this a reality today. It's been an incredible journey, a century of human hours put into this project. So over the course of the years, we've had so many iterations of the rover, from a two-wheeled tail dragger to what you see down below as an iteration with solar panels. And back in the day, some of the earlier versions that Red has talked about, with how much history at CMU has really been incorporated now into this feat. So what is Iris? The biggest driving factor, besides being student-built and student-designed, is that it is 2 kilograms. What is expensive in space is weight, is mass during launch. And so the fact that it's 2 kilograms is paving the way for showing that light, economical rovers can go to the moon, and students doing this is a big deal because it really opens the way to space for everybody.
So I'm Nicholas Acuna. I'm the mechanical lead for Iris. So we designed the rover to be as light as possible, as Raywin was saying, but we also designed the rover to be tough, to be modular, and to survive the extremes of space. So space is a very tough environment to design for. We have to survive very extreme, intense vibrations during launch. When we make it up into space, there are extreme temperatures we have to deal with then. On top of that, many hundreds of degrees below zero and well over 100 degrees Celsius on the hot scale. So we have to survive both the hot conditions and the really cold conditions, all while using very, very little power. So that's why I wrote down cold-blooded here. We have to be able to survive all those different temperature extremes without using power. And on top of all that, we had to pioneer a totally new design, a totally new scale of rover to be able to do all of this while being light. So the design of the rover it's a 4-wheel drive skid steer platform. And the design of that means that it is as light as possible because we don't waste any mass on suspension or on a lot of the luxuries that are afforded by bigger rovers. And you can see here another unique aspect of the design are the ultralight composite wheels, which we took can you pass those around? We took a long time to develop these extremely light wheels over iteration after iteration, from first principles engineering of what does it take, what is a wheel have to be, how do you design a wheel that performs well, and then how can we make this as light as possible in a totally unique design that's never been done or tried. So during the way, as we were building out the platform and we were discovering what we need to do to pull off all these different conditions, we did many different analyses, different simulations. This video right here is a video of a thermal simulation that we did. This one is simulating the behavior when it's outside and in space during the transit, and how we cool down during that transit. So another video here for drive testing. We have a platform that we built that was offloaded so that we are equivalent to lunar weight. We have a lunar simulant that we've used to mimic the terrain, the regolith that can be found on the moon. and we did a number of tests to try to characterize the driving performance, and you can see a few of these here. And this was just another step along the way to make sure that our mission goes as planned. So this is an example of some of the extreme vibrations that we'll see during launch. We won't be able to see what it looks like inside the spacecraft, but this is the kind of intensity that we might have to experience and survive. And to survive that, we had to make the rover extremely stiff and extremely strong. So you can see on the video on the left just how far the wheels might be bouncing if worst case conditions are met, but they still survive. So that's something that we tested again and again, and we analyzed again and again. Another thing we have to deal with is we're drop deployed. So in order to save mass, we don't have a ramp, we don't have a fancy mechanism to deploy us. We just have to survive the drop down to the lunar surface. So this, we made sure the height is equivalent, so we will hit the ground at the same impact velocity, and we did a number of tests to make sure we can survive that landing impact, even if it's on a rock or if it's on a slope. And we also did a ton of work to improve the quality control and quality assurance of the entire mechanical aspects of the rover. So we built our own clean room in multiple locations, and we did composites assembly to aerospace grade level. We did assembly of the rover to a very high level of quality, and we had work plans that were extremely detailed. And yeah, this is just showing some of that, what that looks like. And you can, yep. And this is what it looks like when it's fully built. And this was a picture taken at Astrobotic. And now I'll pass it off to Connor Colombo, who is the avionics lead.
I'm Connor Colombo, the avionics and ground software lead, otherwise generally known as chief engineer. And I'm going to give you a quick overview of our hardware and software systems. So the core of the rover is the flight computer, which has essentially been an unrelenting relay race over the span of basically a decade. It's the core computer that controls everything on the entire rover, and it spans back even earlier than 2017. So this computer got finished basically 3 months before we had to deliver the rover, and it consists of tons of different integrated systems, all of which have to work exactly as designed right away from the get-go. And when you're a team of new people, as we are, basically all students who haven't done a flight computer before, you can expect to drop the baton a couple of times. But the story of Iris is that we always get up and keep going. So one of the things we had to overhaul on this final revision was completely rip out and redo the power system. So basically a whole other separate computer that had to be developed in parallel, and they had to both come together right before we delivered the rover and work. And as we checked out the board and verified that everything happened, all the systems from cameras to imaging to motors basically worked, which was great. But even one tiny flaw is enough to damage the mission. And so 2 weeks before we delivered, when we were going through a battery of important tests to verify the rover, we discovered that the system that basically breaks 2 bolts to drop Iris onto the surface of the moon from the lander would cause us to enter a spin, and we'd end up just hanging from the lander. So we had to undergo an aggressive campaign to completely redesign the deployment system, meet with manufacturers, et cetera, all within that 2-week span. In the end, Iris pulled it off. We went through this aggressive analysis campaign, we put it together, got it on the rover, and made integration day ready basically the day before. But that was only the start of another story, which was the software that goes onto the rover that makes it work. And so once we delivered the rover, we then began a whole campaign of finalizing the software that goes on it. And the software updates happened on the lander as the lander was sort of being built around the rover. And we just finished the final campaign to upload that software, so the rover is now finally ready for the moon as of a couple weeks ago. But software on the rover is only actually one half of the story of Iris overall. There's also software on Earth called ground software, which allows us to communicate and operate the rover from Earth. That software allows us to take images, analyze data on the rover, map and plan operations on the surface, and even reconstruct a 3D model of the environment. Additionally, we have software that allows us to simulate the lunar environment visually and mechanically, so we can allow operators to train before we actually get to the surface of the moon and get those mission operators ready for the surface. Now I'll hand it off to Nikolai Stefanov, who is in charge of those operations.
Hi, I'm Nikolai Stefanov. I am a senior in physics and intended computer science. I am the mission control lead for Iris. I've been with the project for the past 3 years. So, as you've heard today, there has been a lot of effort into getting us to this point, from NASA to the deep history of space robotics here at Carnegie Mellon, and the human century of effort that's gone into Iris alone. That history spans decades, whereas our mission itself is counted by the seconds. It starts as soon as we deploy from the lander down to the surface of the moon. From there, we only have limited battery life in an unknown terrain. Movements are critical. Images contain valuable information that we need in order to make next moves, but we don't necessarily have the time to decide which way to go. That all culminates in training operators. Right now, we're training over 40 students from all over the university, from all over the world, who want nothing more than simply the moon to make the grade with this operation. So, right here, all the commands in this very room you're standing in, all of that will be sent from that computer right over there and be pipelined all the way up over 200,000 miles away. All movements go directly through that. So, what's left? What's still standing in the way? Well, there's still some tests from our rocket provider, ULA. There's still some tests that need to be done for their engines. We need to get integrated or placed on board as a payload, and then fueled and ready by May 3rd, and then launch May 4th. Now, if the miracle of spaceflight happens, if the rover survives the harsh lunar environment that tests say we will, and if we can train operators, if we can come together as a team in this final push, then simply there's nothing else to say other than see you on the moon. Thank you. I'd like to open the floor for questions and then invite the cohort back to help answer them.
Yeah, we can do some Q&A right now. We're also have time for questions and interviews at the end. If there are no questions at this moment.
I do have one or two, if you don't mind. Exactly how long will, if it's been said, forgive my ignorance, how long will the rover be able to operate with its present power on board? I realize it is solar power to an extent, correct?
No, so
Okay, good.
yes, the previous design was solar paneled, but there was a risk of regolith covering the solar panels. So to improve our likelihood of surviving longer, we changed that out for extra battery cells. And so given that, though, it's an interesting take on the better the mission is going. So the more we're driving, the more we're taking pictures, the shorter the mission. So, if all is going well, it could be as short as 20 hours. But in terms of battery life, the longest we expect it to really last is probably up to 50.
You had also mentioned valuable information they're going to be getting from this particular mission. Putting it into layperson's terms, what kind of stuff are we looking for to get out of this?
Yeah, so one thing that's never really been done is such a light rover. So small, light mass, very lightweight. We don't know exactly how that those terra mechanics, so how the wheels and the rover itself will interact with the lunar soil. So really what we're looking at are a couple of different things with that is how does it drive, right? Is there going to be more slip due to that? If the lunar soil is all fluffy after getting after the lander, and so it's not hard packed, is that going to affect, a small rover having that lunar soil cover the top, which was why we were worried about solar panels. Things like that we don't have any real data on for how that lunar soil really interacts with small rovers specifically, or many in general, right? We have the Chinese rover on there right now and the Soviet rover from way back when, but that data isn't necessarily relevant to US rovers. And so there's a lot of lunar surface data that we'll be getting, as well as showing that rovers of this size can survive, because that's always been a big question with the space community, is if something this size really can survive, is useful for being able to send up multitudes of these for the same cost as one rover, one large rover, and can do a lot more in that sense.
As a child of the 70s, I remember very early moonshots and so forth, and of course I grew up with the space shuttle. And one of the things we heard about when I was a kid was the Sea of Tranquility and so forth. So understanding that a certain group of people may understand this, just where on the moon is it going to land?
So our current, ours is actually going to be closer to the equator. We are going to be up right around here in the, I do not know.
Great-sized domes.
Goitism domes, thank you. The German word always messes me up, so I appreciate it. But our next lunar rover, Moon Ranger, that's going, Carnegie Mellon is sending another one, and that will be at the South Poles, and that will be looking for ice, actually. So it's something that Iris is really leading into those next rovers, including ones at Carnegie Mellon, and pushing that direction.
Just insane. How far up? I'm sorry.
I was just going to quickly ask, is that secondary rover the same design as this one?
It is not. It's very different, given that it has a NASA payload for searching for ice, but it does use carbon fiber similarly that we looked into original research-wise with Iris. I think these are questions, though, that would be good for one, Red to really answer to, and two, possibly future questions. But Iris, a lot of things on Iris, like the carbon fiber and things, did feed into that design, as well as a lot of lessons learned from the Iris program.
So could you just spread a little bit so that
Yeah,
people can
this
see?
one.
So the lower right is CMU's next rover, next mission. This one's the size of a suitcase. It is very much more massive, but because of low gravity, it's only 7 pounds on the moon. This one is solar. This one has a lot of power capability. It has an exceptionally powerful computer, and of course the kind of software that Carnegie Mellon can bring to the game. This one will roam afar, and its purpose will be to characterize and measure the water ice at the pole of the moon. And this is viewed to be the most valued resource in the solar system.
Is there a name for the rover?
Moon Ranger, one word.